has the highest value. Well, which element has highest local degree? 2. Yeah. So second element have 5. Yeah. And that's why here it will get the first place. Yeah. So let's see which element has the next highest. So we see that these are the next, yeah, like winners. Yeah. So here we assign second place for all of them. Yeah. Next, we check the next highest value, 4, 5, 6. Yeah. So these 3 elements will get the third place, and these 2 will get the last. Yeah. Place number 4. Yeah. I think the idea is clear. Yeah. So you check which is the highest one. For that you give the first place, and then you check which is the next. Yeah. So in this way you find this first type of the round. The first place and the last 4th place. So this was this first, the most simple method. The next, we need the second round. Yeah, that I said is based on reachability matrix. And no matter which method we will use in the first case, the second method or this second round won't change. Yeah, it will be all the time based on this reachability matrix. So in every kind of step, anyway, you will stick to these values. Yeah, they won't change. So what we do, we take reachability matrix those elements. Yeah? So in this way, we find this reachability component for each of the nodes, and then we divide this reachability component with the number of nodes. And in this way, we get the values, and then again, we kind of rank them. So let's see on the same example how it will look like. So like I said, we count values 1 in each row to find the reachability component or this Ri. So here will be 2. No? So here reachability component is 2. 1, 3, 2. 1, 3, 2.
3, 1, 5, 5.
Yeah. So 3, 1, 5, 5, and 5. So now we will divide it with the number of elements. So on the small matrices, when you have just few connections, you could easily maybe assign those ranks based on, let's say, it has 5, it will get the first place, yeah? But imagine when you have large graphs, yeah, with thousands of connections, then those numbers will be very high. And to work with those numbers and finding their places, it could take a lot of resources from the computer. That's why we can, let's say, convert these values to the scale from 0 to 1. And that's why we divide it with the number of elements. So here will be 2 divided with 9, 1 divided with 9, 3 with 9, 2, 3, 1 with 9, okay, 9, 5 with 9, and also 5 with 9. Anyway, no matter those results, so these will get the first place. Yeah, because the reachability component in this case is the highest one. The second will go to 3, 3, yeah, which was, yeah, it will be the second place, 2, 2, the third, and last place, yeah, 4th place. So I will show it to you better. Now I will delete the screen. Yeah, so it looks like this. Yeah. Like I said, if you had there thousands, yeah, you need for the reachability components. In this way, you would convert it from 0 to 1. Yeah, this scale will change. And working with the values from 0 to 1 for the computer, of course, will be easier than with the thousands, yeah, to process them and go through each of those values and compare which is the highest one and which is the smallest one. Yeah? So the first place, second, third, and fourth. Yeah? So in this way, we find this second rank. And like I said, this won't change. Yeah? No matter which method we will use in the first, for the first rank, rank 2 will be the same. So first and last place is here. Yeah? Next step, like I said, is like to combine those ranks together, yeah, to find this overall place. Yeah? And what we do, we take those ranks from the first method, ranks from the second method, and we just like sum them together. And in this way we get those summed ranks. And now, what we do now, we assign those final places. And now the idea is like a bit opposite. The smallest value will get, yeah, because let's say these elements got like the highest places overall, yeah. That's why, let's say here we have 3, 3, 3. It's the smallest, yeah. So in both methods, these elements, they were like a winners, yeah. And that's why we will assign first places like to the smallest overall ranks. That's the idea. And now 3, 4, 5, yeah. 5 is the next. Second place. 6, 3, 3, and 4, 4. So these are the final total ranks based on both methods. Remove this. So far, is the idea clear? How we get all those values? Okay. What we do next? So we have those ranks. Like I said, we can already calculate the structural importance and also dispersion of the ranks. Yeah. So here, this is overall results. So how we calculate structural importance? So we calculate this importance for each of the elements. Yeah, first of all, this is important. And we need like total rank, yeah, of the element, of the particular element. Like for the element number 1, what was the total, this rank, final rank, yeah? Our max will be maximum rank that we have in the structure. So in my case, there was 4. 4 was maximum, yeah? And element, let's say, with this maximum value of 1 will be the most important, and with the smallest value, not 0, yeah, but something more than 0,